Hello, this is lecture 1-stat135. Today we went over the syllabus and did an introduction to parameter estimation and confidence intervals. So some syllabus highlights. 134 is a prerequisite for this class, non-negotiable prerequisite that is. Stat 133, you really only need the first months, and that's a co-requisite. You need to know some basic linear algebra and multivariable calculus, including so that's enough said there. Please bring a laptop to classes that will occasionally be doing some R exercises in class, and lab starts this Friday, and homework is going to be due most every Friday. We'll be passing out the first homework on Friday. So we started off with asking which of these two scenarios represent statistics, and you said correctly it's the first one. So notice that probability is where you know the contents of the pail, and you, for example, ask a question like, what's the probability that I get at least a marble of each color? Whereas in statistics, which is often thought of as inverse probability, we don't know the contents of the pail. We take a sample and we try and infer what the content is. So we start off with just an introduction. A lot of the ideas that I give here we're going to derive formally, but I just want to give sort of an overview. So in particular, let's talk about sampling with replacement. So you toss a coin 100 times and you get 45 heads. What can you say about the probability of the coin landing heads, P? So the answer is that you can give an estimate, P hat for P, and as well a 99% confidence interval for P. So here's how you would do something like that. So you have a box here, 0, 1 box, and chance P for heads 1. We draw 100 tickets with replacement, x1 to x100, and our estimator is going to be the sample mean, which is 45 out of 100, or 0.45. So there are many different estimators you can use. There's parametric and non-parametric estimators, and we'll talk about all of that good stuff, but here is just a natural estimator. So this estimator we'll see is unbiased, which means that on average it's going to be the same as the true parameter. So P hat, it is a random variable and it has a distribution that's called the sampling distribution. So in this case, if we have a sample size of 100, then the sample mean is going to be approximately normal by the central limit theorem, and we wonder what's the variability of P hat. That's called the standard error. So because we know all about the variance of the standard of the sample mean, we can just write that as the variance of the formula for the mean. We can just pull out the constant and we get a formula here. And furthermore, because it's a 0, 1 box, x is binomial 1p, or Bernoulli. The variance is p times 1 minus p, which is quadratic, and in fact it's quadratic upside down. So the shape is given here in this graph of the variance of x as a function of p, and you can see that it takes its maximum at a half, at which case the variance is a quarter. So the standard error is always going to be less than or equal to the standard error is always going to be less than or equal to the square root of the variance over 100, which is square root of 1/4 divided by square root of 100, or 0.05. So now a conservative estimate of the standard error, so the standard error is always less than 0.05, so we'll say that that's a conservative estimate. And a conservative estimate of a 99% confidence interval is given by the formula here, where z 0.005 is the 99.5th percent quantile of the standard normal curve. So we will derive all of this in time. So we get this interval here, and you can also bootstrap the standard error. So that in this case just means replacing p, which is unknown, by its estimate p hat, and so we see we get something quite close to 0.05. And so we can then also find a bootstrap estimate for the 99% CI. And a conservative estimate is better if you can find it, but it's actually quite rare that you can find it, because we don't always have a formula for the variance of the sample distribution. So in summary, we're discussing a dichotomous case where our box is a 0-1 box. P is the proportion of ones in your box. We draw a sample of size n from a box with capital N numbers. Our estimate is the sample mean. A bootstrap SC is given by this formula here, where now P is substituted by P hat. And a conservative SE is 0.5 divided by the square root of n. So what happens if we draw from a box without replacement? So now our xi are not independent anymore. And we'll derive this formula here. We'll see that we have to introduce a correction factor. And this will come, you can read about this in the book, page 214 in Rice. So for example, if we have a box size 5 with 1 1 and 4 zeros, so we draw 2 without replacement. So I asked you to list all the possible samples that we can have, then compute the corresponding estimate and make the sampling distribution by hand. So here it is, and then also to compute the mean and variance of the sampling distribution. So that's all given here. The expectation of p hat corresponds with p, which is 1/5. So again, that's because p hat is unbiased. And the variance, just using stat134 formula for variance, turns out to be 0.06, which agrees with our theory involving the correction factor